Hello, everyone. And the next talk in the PD session is given by Professor Pierre Cardaliaguet and Professor Francois Delarue. Professor Pierre Cardaliaguet is a professor at the University of Paris-Dauphine. He's a leading expert in optimal control and differential games, and in PD and calculus of variations. And Professor Francois Delarue is a professor at the University Denise Sophia Antipolis. He's a leading expert in statistical analysis, probability, and PDE, and in mean field games. Today, they will give a general presentation on the mean field game equation. Together with J.M. Lashley and Pierre Lyons, they made a breakthrough and proved a milestone result on the mean field game. That is to resolve the convergence problem. Today, they are going to present these wonderful results. The title of the talk is The Master Equation in Mean Field Games. So please go ahead, professors.
Hello, Francois and I would like to thank the scientific committee for inviting us to present our works on the master equation, which is a partial differential equation arising in some mean field problem, namely called mean field games. Mean field games are optimal control problems with infinitely many agents, each agent controlling her state in order to minimize the cost, which depends on the other position, and the other position are the other agent's position are infinitely many in the sense that each of them has a negligible influence on the global system. This kind of model were first introduced in economy under the terminology of heterogeneous agent models, and then rediscovered by Lasry and Lyons on the one hand, who gave the terminology of mean field game, and Wang, Keynes, and Mallarmé, who used this kind of model in engineering problems. So to have a gross idea of what is a mean field game, you can think about a traffic jam in which each car wants to go as fast as possible, but has to take into account the presence of other car, and you see that the presence or the absence of a car does not make much difference in this traffic flow. So let's start with what are the n-player problem in this kind of models. Capital N is the number of players here. T is the time horizon, so the game is going to be played on 0t. And player I wants to minimize her costs by using her control alpha t, and the cost takes the form of an expectation of an integral between 0 and t plus a terminal cost. The integral is made on a kinetic cost, which is the square of the control, plus an interaction cost. So here, xi that you find here is the position of player I at time t. So this is the cost for player I, there is xi, and the interaction with the other players, mni being the empirical distribution of the other players. So you see the sum for j not equal to I of xjt divided by n minus 1. And the terminal cost has the same structure as the cost with f. It involves another function, possibly another function g at terminal time t. So the link between the position of player I and the control is the stochastic differential equation, which says that the drift of xj is just the control alpha j, and xj is perturbed by two kinds of noise, which are here independent Brownian motions, a specific noise for player j, wj, and a common noise to all the players, which is denoted by w naught. So this common noise is important in economy, where some random factors affect all the economy. So what we're interested in here, the good notion of optimality is the notion of Nash equilibrium. So we say that a tuple alpha bar 1, alpha bar n is a Nash equilibrium if, when I am player I, if I choose alpha I instead of choosing alpha bar I, so if I deviate, then my cost increases. So how to find this kind of Nash equilibria? So to do that, we need to specify the information structure available to each player. And here we work with closed loop control, meaning that the player alpha, the player I has to choose her control in function of time and of the distribution of the other players, of all the players, the position of all the players. So what we call the value function here is the minimal cost you can ensure through Nash equilibrium at time t, and when the system is at position x, so meaning that player 1 is at position x1 and player n is at position at xn. So this function Vn, I satisfies a partial differential equation, which is, so it's a huge partial differential equation because there is an equation for each I. So there, and it's stated in the whole space, meaning time and the position of all the players. So we here, I didn't say it yet, but we are in RD, and each player contributes. So it's in RD to the power n. So this is a backward equation with a terminal condition, which is the cost, the terminal cost, and ln involves the local cost, capital F, plus nonlinear derivatives, which are related to Ito's formula and dynamic programming. The interest of the Nash system, which gives uniquely the solution, the family of solution Vni, is the fact that it also gives an optimal way for players to play, namely to find the optimal control, control. We just need to take the derivative with respect to I, to xi, or the function Vni. So this implies that the optimal trajectory are driven by a system of stochastic differential equation in which the optimal path for player I has the dynamics with the drift, which is given by the derivative with respect to xi of Vni, plus the noise that I described already, the individual noise and the common noise. So what we are interested in field game is the behavior as the number of players tend to infinity of the value function Vni, so the solution of the Nash system on the one hand, and on the other hand, of the solution, the behavior of the solution of the optimal trajectory. Of course, this kind of models looks like standard weakly interacting systems, particle systems, except that here the interaction between the player is quite involved. Also, the symmetry of this system implies that the xn are exchangeable. So what I'm going to describe now is the formal limit of this system and of the Nash equilibrium. So let's go back first to the problem each player has to solve. It has to solve it has to minimize this kind of quantity, but now in Nash equilibrium setting, that is, the controls alpha j now are fixed, are given by alpha bar j. So what one can expect is the fact that the Mni has a limit as n goes to infinity and stabilized to something which is actually independent of I, because in this expression, the contribution of each player becomes more and more neglectable. So we expect that Mni of xt is going to converge to some measure mt. So this will give rise to an optimal control problem where mt is fixed, but then we need to keep track of the fact that we are at optimum, so the Mni was the distribution of the optimal path for each player. So this leads to the probabilistic formulation of what is called the mini-field gain problem, that is the limit problem as n goes to infinity. So to describe this probabilistic formulation is made in two parts. So first, we fix a flow of measure mt, which is in principle the limit of the MMT, and so each small player, player I, for instance, minimize the resulting cost in which we replace the empirical measure by the measure MT. And the state of the problem is, as before, given by as a drift the control and the independent noise and the common noise. But on the other hand, we need to keep track of the fact that MT comes from the limit of empirical measure. So once we have this control problem, we find the optimal solution, and remember that the MN were made of optimal solution, which means that we say that the Nash condition holds if MT is just the condition law of the optimal path given W naught. So this is a fixed point formulation in the sense that given MT, we find the optimal path, and given the optimal path, we find MT as a condition law. There are two other formulations for this problem, which are both involving partial differential equations, the master equation, which gives a name to the talk, and the mean field game system that we will describe when we study the master equation. So for the master equation, a heuristic way to see it is to go back to the Nash system, so this system of partial differential equations, which were backward in time, and to look at its symmetry. This system has a unique solution, so the symmetry of the system is preserved. It turns out that each Vni can be written as a function independent of I, capital Vn, depending on time, xi for player I, and the distribution of all other players, so the empirical measure of all other players. And the master equation is a formal limit of the equation satisfied by capital Vn. The mean field game system will be the limit of this kind of problem, but I will describe it later on. So the master equation, as I explained, is a function, has an unknown, which is a function of time, space, and measure. So we are in RD, so space is in RD, and the measure in this probability measure on RD. And it takes the form of a backward equation as a Nash system with a terminal condition exactly as in the Nash system. And this backward equation involves derivatives in space, but also in measure. And we will explain what is the meaning of this derivative with respect to the measure later on. And the operator L is the limit of the operator L and I, which were involved in the Nash system. And we will describe them later. So the goal of our work, and in particular the one we described in this talk, is on the one hand, the analysis of the various mean field game equilibria and various formulations, so probabilistic formulation, master equation, or mean field game system. And on the other hand, to derive this system from the n-player game, so the Nash system, as n goes to plus infinity. So this is what we are going to describe through two parts for this talk. So on the one hand, the monotone regime, in which we will see that the master equation has a classical solution, which allows us to derive the convergence of the Nash system. And on the other hand, the more recent result on what happens outside of this regime of smoothness. Okay, so let's first fix some notation. So P1 will be the set of Borel probability measure with first order moment. It is endowed by the Monge convergence distance, which is defined classically as the supremum over one Lipschitz function of phi integrated against the difference of the measure we want to, the measure m and n prime for which we want to compute the distance. And we look at two notions of derivatives. So remember, the master equation involves derivatives in the space of measure. In fact, the intrinsic derivative. But to define this intrinsic derivative would be more convenient for us and for later use to introduce the directional derivative. So the directional derivative is simply the limit of the quotient when we fix the measure m, and we perturb it by a Dirac mass sitting at a point y in Rd. So if we look at this quotient and we assume that this limit exists and is continuous and in both variable and bounded, then we say that the function u is C1. So it's not difficult to check that this condition, this integrability condition holds. And in fact, it's used at the end of the talk. On the other hand, the intrinsic derivative is defined from this directional derivative simply as a derivative respect to the extra variable of the directional derivative. So in order to build the solution to the master equation, we will need uniqueness of equilibria in mean-field game. Unfortunately, this does not hold in general, and we need to enforce some condition for this. And this condition is the Lasrelians monotonicity condition. So it was introduced by Lasrelians in their earlier work on mean-field game, and it says that the map F, and it will be also imposed in the terminal cost of G, is monotone if the integral of f minus f n prime against n minus n prime is non-negative for any measure m and n prime. So typically, this kind of cost is a perturbation of monotone cost, and indeed, the heuristic interpretation of the monotony is the fact that the cost is high when the density is high, which has a stabilizing effect. And we will expect that the mean-field game equilibria is unique when f and g, so the interaction cost, are monotone. So let's now talk about the master equation, which is the main object of this lecture, and let's describe it a little bit in detail. So in the master equation, let me remind you that the unknown is a scalar function depending on time, position in Rd, and measure in P1 of Rd. And it takes the form of a backward equation of parabolic type, so for some part, so involving Laplacian respect to x and Hamilton-Jacobi term here also with respect to x. But also, and this part is very typical of optimal control, but there are also interaction parts related to the M dependence, which shows the impact of the players on the value of a typical player. So there are linear terms of second order, which describe the impact of the noise, so the player. So this is individual noise, and when you see beta, this is the common noise. Okay, it's in part of the common noise, the impact of the common noise. And on the other hand, there is a drift of the other player, which is encoded here. So if you remember, I told you that the drift was the derivative of the value function. So it is here, which impacts the function u through the m derivative. So this is a non-linear, non-local because of this term equation, and actually we will see in a moment that it is of transport type. So one of our main results in the joint work with Francois Delarue, Jean-Michel Lasserie, and Pierre Cardaliaguet is to prove that under suitable regularity condition on f and g, they are smooth in x and n, and if they are monotone, then the master equation has a unique classical solution in which all the derivatives exist and are continuous. And in fact, the monotonicity property is preserved along the flow in the sense that u of t is always monotone for any time. As we will see in a moment, this implies the convergence of the mass system, the existence of such a solution. So let's briefly describe how one can prove this result. It is based on the method of characteristics. So in this sense, we are dealing with the transport equation. And here the characteristics are random. So let's fix an initial time t0 and initial measure m0. Then we will define capital U of t0 m0 as the value at time t0 of this function u. So here, u M and actually and V are solutions to this system. So U is a solution of a backward Hamilton-Jacobi equation, which is stochastic because it involves W naught as common noise. And it takes this form, and V here is here to ensure that the backward equation for U has a solution which is adapted to the common noise. M satisfies a more classical Kolmogorov or Planck equation, which again is stochastic because of the common noise, and which has for drift, again, the derivative of the function, the value function. So U is a typical, is a optimal cost of a small player, while M is a distribution of players which evolve in time randomly because of the common noise. And the initial condition is T naught M naught fixed for M, and as usual is the function G for U. So if we set capital U through this formula, it's relatively easy to check that capital U is a solution of the master equation, and this is related to some ethos formulas that we developed in this context. The difficult part in this construction is, on the one hand, to prove that the solution of the mean-field-gain system, so the system MFG, exists and gives rise to a function U, which is smooth enough, in particular in the measure variable, to justify the computation. So this is what I'm going to explain now. So briefly, how do we build solutions to the gain system? Well, there are basically two cases. The case where beta equals 0, so in which case the system becomes deterministic and V is simply 0. And this was well known. In fact, this solution was built by Lasry and Nyons in their early works of 2010. Now, the solution is built by compactness technique using the parabolic regularity of the system and fixed point argument, because you see that U depends on M and M depends on mu. So you need a fixed point argument to ensure the existence of solution. Existence of solution is ensured even without monotonicity, and monotonicity gives the uniqueness of the solutions to this system in this setting. When beta is positive, the system is much more challenging because compactness techniques are not available, and one needs to rely on continuity argument. So taking eta small first and then increasing eta, and using the stability of the system given by the Lasry-Lyons monotonicity. So once we have the existence of U and N, this defines the function capital U, but does not ensure its smoothness. And to get this smoothness, it's done by linearization, and we establish regularity of the flow generated by the system MFG by using the monotonicity. So now it's time for me to let the floor to Francois. Francois, it's your turn.
So indeed, the question now is to see how we can use the master equation to address the large M behavior of the solution to the M-player system. So in order to do this, let me first recap a few notations that we used before. So these are the dynamics of the players in the M-player game, and these are the costs. And the very first question is that we want to study the large N behavior of the values. And the philosophy to do that is pretty simple. What we want to do is to compare the shape of the Nash system for the values with the shape of the master equation for U. This is the shape of the Nash system. So this is the expanded version of the operator LNI that we had before. And in fact, if you have a look carefully at the structure of the Nash system, you will recognize the same form as in the master equation. You have some blue terms connected with optimization, and you have some red terms connected with the weak interaction. So precisely here you see that this is the same Hamiltonian as in the master equation. And this term is driven by the equilibrium velocity fields to the players J that are not equal to I. And I is the index for the value function V and I. As for these two terms here and here, they come from the noises. So this one comes from the action of the proper noise to player I, and also the noises to the other players J onto V and I. And these ones come from the action of the common noise onto the value function V and I. So this is the second result that we have in the book with Lasserie and Lyons in the periodic setting, and then this is extended to the Euclidean setting in the book with Carmona, under the same regularity assumptions as before, and under the Lasserie-Lyons monotonicity condition. We have an upper bound on the distance between the V and I's and the solution to the master equation. So here you see that we compute V and I, so for one player I at Tx, where bold X is a tuple of initial states for the players in the system. As for the solution to the master equation, this is computed at the private state xi for the same I as in V and I, and the state of the population is the empirical measure of the x's. And you see that the bound that we have is typically of size 1/n. The proof is not easy. The difficulty is that we have, or we don't have, uniform estimates in n of the regularity of the V and I's. And so instead we have to play with the fact that capital U is smooth. And in fact, once we know that capital U is smooth and we have the proper or the private noises, the proof works, meaning that there is no need of monotonicity as soon as you have these two features. Another result or another question is, once you have the convergence of the values, what about the convergence of the trajectories, which is a natural question from a probabilistic point of view. So these are the equilibrium trajectories for the n-player game. So this is the trajectory for player I. This is driven by noises Wi and W0, and the equilibrium velocity field is minus the derivative of V and I in the direction I. And you write down the same equation for the mean field game. So the solution is y1, yn instead of x1, xn. You couple the two systems with the same noises, Wi, W0, and with the same initial conditions. And now the key point is that you replace, for the velocity field, the derivative of the V and I's by the derivative of U in the direction x. So x, it is the private state. Here, this is computed at x is equal y and I. And you compute, or you use as state of the population, the theoretical law of y, given the realization of the common noise. And this is our next result in the same references as before, and there's the same assumption. So you have an upper bound for the distance between the x's and the y's. And you see that the bound depends on the dimension, which should not be a big surprise. And this is typical of the results that you have in probability theory on the rate of convergence of the empirical distribution of an IID sample towards the theoretical distribution of the sample. Also, if you remember that the y's are independent, you see that the x's become independent. When I say independent, I should say given the realization of the common noise, and this is a form of propagation of chaos. The proof relies on an auxiliary interacting particle system that is in between. So this is exactly associated with the dynamics of the y's. So the y solve Mac-Inversov equation interaction with their own law. And now you introduce the y tildes, which is the weakly interacting particle system associated with these Mac-Inversov equations. So in brief, what you do is that you replace the theoretical law by the empirical measure of the system. So the empirical measures of the y tilde s. And our main result in the proof is to show that the distance between the x and the y tildes is of order 1 over n, which is much, much better than the distance between the x and the y's. And this result is very useful. It allows you to push further the analysis and to have some fluctuation and deviation results. In short, it suffices to study the deviations and the fluctuation for this weakly interacting particle system on the y tildes. A few sketch of the proof of these statements, at least for the value function. The idea is to project the solution of the master equation on the space Rd to the n. So what you do is that you take a bold X tuple of elements in Rd to the n, and you compute the solution to the master equation at the private state xi, and so you put a label I in the left, and at the empirical measure at the x's, except xi itself. And so you denote this by u and I. And then you have a very nice dictionary that allows you to compute the Euclidean derivative of this u and I in terms of the Wasserstein derivative of capital U. For instance, if you take the derivative in direction j not equal to I, this is 1 over n minus 1 times the Wasserstein derivative. And this is very useful because now what you can do is that you can expand the Nash system or the operator LNI in the Nash system along U and I instead of V and I. And what you do is that you see how far U and I is from a zero of this operator. And then the result is that you get a remainder term that is called Rni here, and the size of it is 1 over n. So in the end, you have capital N equations. The remainder in any of these equations is 1 over n, and you have to see how this 1 over n propagates between the n equations. And the strategy is to take the equilibrium trajectory xn, you expand the VNI, the original values, the UNI, given by the solution of the master equation, they expand as backward stochastic differential equations. And by using the presence of the private noises, you can use some stability properties for backward equations. A few extensions, so you can find further analysis of the master equation for other forms of mean-field games with local interactions, with finite state spaces, with mean-field interactions on the controls. You can find further solvability results on the master equation for weaker coefficients, meaning that less regular coefficients, but still in presence of monotonicity. Or you can find other form of monotonicity. Further questions, what about numerical approximation? What about long-term behavior? What I would like to do next is to talk about what happens outside monotonicity. First question, what happens to the equilibria themselves? So generally speaking, if you remove monotonicity, you lose uniqueness. But existence may remain in many cases. And the key point is to use compactness, or this is one typical strategy. Without common noise, this is pretty standard. With common noise, this is a bit more subtle because the space on which you define or you study compactness is much, much wider. And then in the end, what you get is weak equilibria, meaning these are random equilibria because of the presence of the common noise, but the randomness of an equilibrium can be larger somehow than the randomness of the common noise itself, which is a phenomenon that is typical of weak solutions to stochastic differential equations. What about the master equation? If you lose uniqueness, then you expect to see some singularities, and this makes the analysis very difficult. I will try to get back to this point next for one class of mean-field games. What about the convergence problem? Well, there was a major breakthrough by Laker and Fisher a few years ago. By compactness argument, they study weak limits of Nash system, and they prove that those weak limits are weak equilibria for a notion of weak that is very close to the one I mentioned before. The difficulty is that you know very few about the controls. So you have to use a weak topology on the control, but at the same time, you need to quantify the asymptotic influence of one player on the rest of the population. The link with the master equation for the convergence problem is not clear, except in very specific cases. So now I would like to see what happens outside monotonicity for a given class of mean-field games. And to introduce this given class of mean-field games, I need to introduce another problem, another optimization problem that is related to the game itself. So instead of having a model with competition, I will have a model with cooperation. So what I do is that I use the same dynamics as before, but the shape of the cost functional is not exactly the same. Before I had the kinetic cost to one player, now I make the mean over all the kinetic costs. Before we had the interaction between the states of one player and the rest of the population, now we have an energy on the whole state of the population. And in the end, what we want to do is to minimize this global cost to the society. So this is not exactly the same problem as before, because we no longer have a look at compromises, but at a global minimizer. But there are some similar equations. What about the shape of the values when n tends to infinity? What about the shape of the optimal trajectories? For instance, the value, this is the definition of the value when the initial time is 0 and the initial state is some bold x as before. What about the asymptotic problem that we should have? This is no longer a mean-field game, but we speak about, or we talk about a mean-field control, or also an optimal control of the making-does of type. So basically what you do is that you take one typical player in the population, you compute its own kinetic cost, and you replace the mean field or the empirical measure by the theoretical law of this player given the realization of the common noise. And then what you can do is to define the value function here at the initial time and for a given initial state of the population. If the value function is smooth in time and space, then you expect to have a classical solution to a Hamilton-Jacobi equation on the space of probability measures. And I'm going to write down this equation next. If F calligraphic and G calligraphic are convex on the space of measures and are smooth, then indeed I have a classical solution. What about the connection with games, with mean-field games? This is what we call potential mean-field games. So we consider a class of mean-field games for which the interaction cost in blue F and G derive from energies on the space of probability measures. So you see for F, the derivative of F in Y is in fact the Wasserstein derivative of some potential, some energy on the space of probability measures, and the same for G's. The connection between the control and the game, well, the minimizers of the mean-field control are equilibria to the mean-field game. There is no converse. What about the connection with the master equation? When F calligraphic and G calligraphic are convex, the blue F and G are monotone in the same sense as before. And then if the data are smooth, you can have a look at the master equation at the value. And then the solution to the master equation derives from the value of the mean-field control. So you have this equality in red, which is exactly the same as what you have here for the data. Now we would like to see what happens when you remove convexity on the energies, equivalently when you remove monotonicity on the interaction cost. If you do this, certainly you lose the fact that the value to the mean field control is a classical solution to Hamilton-Jacobi. But you're not that far. This is one first result of Pierre with Takis Souganidis under some nice regularity assumptions of the data, but without convexity on the energies F and G. The value of the mean field control is global Lipschitz, and even more, there is an open dense subset on the state space 0t times P1. P1 is the space of probability measures with an expectation, on which you have that the value is a classical solution. So meaning that at any point of O, you have the Hamilton-Jacobi equation, and this is the shape of the Hamilton-Jacobi equation. So this is the Hamiltonian, this is the energy, and this term comes from the private noise in the dynamics. I have to say that in these slides now, beta is equal to 0, so there is no common noise. You just have the private noise in the dynamics. So you have the Hamilton-Jacobi equation at many, many points, and you can wonder about uniqueness. And in fact, you can force uniqueness by restricting the class of solution to the Hamilton-Jacobi equation. So this is another result that we have with Adekos check-in under nice regularity assumptions on the data without convexity in the periodic setting. So you are working on the torus. You can find a probability measure on P1 such that if you have a solution of the Hamilton-Jacobi equation almost everywhere, so almost everywhere in time and space, and if this solution is displacement semi-concave, then this is the value. This is equal to calligraphic U. So you have uniqueness. What about displacement convexity? It means that this is convex along geodesics on the space of probability measures. And what about the use of semi-concavity? This is reminiscent of what you have for Hamilton-Jacobi equations in finite dimension. And you have very nice papers about uniqueness to Hamilton-Jacobi in finite dimension by Khrushchev and Douglas in the 60s. In fact, for sure, you have some results in finite dimension about connection between viscosity solutions and almost everywhere semi-concave solution. Here you have to see that the analysis of viscosity solutions is not easy, especially because of this additional term. I give you some references at the end of the slide. So these are results about the Hamilton-Jacobi equation for the mean field control. What about the large M behavior of the value to the N control problems? So this is another result of Pierre and his collaborators. So you have the distance between the value of the N control problem with the solution to the mean field control problem, and the distance between the two is of size 1/n to the gamma for some exponent gamma depending on the dimension. And the proof works without convexity on F and G and uses a lot semi-concavity. And in fact, coupled with theorem 6, you can have propagation of chaos for the optimal trajectories starting from the same set O as in the statement of theorem 6. So now back to mean field gains.
Just 1 minute left.
Here is another statement with check-in in the same setting as theorem 7. And so for the same probability measure P as before, if you take the almost everywhere derivative of the value function of the mean field control, then this is a weak, in the sense that should be specified, solution to this equation. The black part of it is exactly the master equation. And the red term here, this is a normalization constant that is consistent with the fact that this derivative must be of 0 measure with respect to M. So this is almost the master equation. And in fact, this is the delta over delta M derivative of the Hamilton-Jacobi equation for the value function. And even more, you have a uniqueness result in the sense that any weak solution to this equation derives from a potential. And if this potential is semi-concave, it must be the value function. And then you have uniqueness. And this is a generalization of earlier results by Khrushchev in the 60s in finite dimension. Now, as a conclusion, a few perspectives. So you could wonder about the existence of classical solution to the master equation outside monotonicity by using some possible smoothing effect of the common noise. You could wonder about the equilibria that should be selected when there is no uniqueness and having some selection rules. And then you could wonder about proving that those selected equilibria are indeed the limits of the n-player equilibria from the n-particle system. I thank you for your attention. Thank you.
Thank you. It's a very good talk. Thank you. Thanks a lot. I think it's exactly the time we finished in the time.